Okay, so we're looking at the start of chapter 9 here. So we're looking at reactions in solutions. So up till now, we've been talking about different types of solutions and concentration of solutions, but we haven't been talking about different solutions that are doing a chemical reaction yet. So we haven't even seen any chemical reactions yet this unit. So what we're looking at here is when you have, let me just adjust this here. Okay, so whenever you have a double displacement reaction, typically you have two aqueous solutions that are reacting, right? So you'll have something that's aqueous reacting with something else that's aqueous most of the time, right? And you have two different compounds. So normally there are two outcomes that can happen. You're either going to have a reaction occur, which means that there is a visual or some sort of measurable observation. And we did talk about this in Unit 2 when we looked at double displacement reactions, but we're going to recap it here. Or no reaction happens, which means that nothing occurs. None of the possible observations are seen. So there are three clues that tell us that a chemical reaction has happened in a double displacement scenario. So first of all, if a precipitate is formed, so that means you have at least one or more solid products. Okay, so we can see that as an example here. So meaning we have two aqueous solutions that are mixed and one of the products is a solid. You could have both becoming solid, but having just at least one gives us a visual observation. Another scenario that will tell us that an observation is made for a chemical change is if you see gas bubbles, right? So if we see gas bubbles, we know a chemical change has occurred. The third one is if we have a neutralization happening. So remember, neutralization is where you have an acid reacting with a base, which means that the products end up being neutral, which is a pH of 7. Okay, so the most common form will be a precipitate, but of course any of these are technically evidence that a chemical reaction has happened. So let's review, how do we know from the solubility table? So remember, in order to determine if your products have high solubility or low solubility, you are looking at the solubility table, right? So high solubility compounds, we're going to have a state of being AQ, which means that it is still fully dissolved. Low solubility compounds we would put as an S, which means that we have that as a precipitate, right? So first you would look to see what column you're working with. So let's say we had calcium sulfate, right? So you would look to see, okay, sulfate is in this column, and then you're either looking to see, is calcium in the top row or is calcium in the bottom row? So in this case, calcium is in the bottom row, which means it has low solubility. So calcium sulfate is an example of where we would put an S. So if it's not found in your bottom row, obviously it would fit in the top row. So if this was potassium sulfate, let's just say, for example, potassium is not down here, so it would automatically be a high solubility compound. Okay, so what we're learning here is how to write a new type of equation. Okay, it's very similar to one you've already done, actually. It has to do with dissociation. So first we would write the ionic equation, then the net ionic equation. So this won't make sense until we start doing some examples. So first of all, what is the purpose of writing these equations? Essentially what we want to show is the dissociated form of all soluble compounds. So what does that mean? So when we have something that has an AQ beside it, really that means that this compound is fully dissolved. So if you remember that when we looked at dissociation equations, technically when that's dissolved, it's really sodium ions and chlorine ions. Once an ionic compound is dissolved in water, the ions are separated. So these types of equations that we're going to be writing out today are showing the separation properly, how it actually would behave when it's in water. The net ionic equation is essentially removing ions that are not participating in the reaction. So those are called spectator ions. So all spectator ions have high solubility, and they're not really involved in the change that is happening. So this will make more sense once we look at an example, and then I'll come back to this concept. Okay, so we're going to write the balanced chemical equation, or balanced chemical reaction, the ionic equation, and the net ionic equation. So we're going to write three different reactions here. So we have a solution of lead 2 nitrate and solution of potassium iodide are mixed. So here are our reactants. So we're going to start off with the balanced chemical reaction. So let's name this like maybe A, B, and then our ionic is going to be C. So we have lead 2 nitrate, and it tells us it's a solution, plus potassium iodide, and it says that they are both solutions. So we have a double displacement reaction. So the lead and potassium are going to swap. So now I have potassium nitrate and lead 2 iodide. So remember, you're always doing the crisscross rule. Okay, so let's look up on the solubility table what our states are going to be here. So let me erase this so we can go through this together. Okay, so one of them was potassium nitrate. So nitrate, actually nothing has low solubility with potassium nitrate. So meaning it's going to be in this top example here, like everything with nitrate has high solubility. So here I know this has high solubility. Lead 2 iodide. So iodide is here. And actually lead 2 is right here. So this is going to have low solubility. So over here, I have a solid. And now, of course, we have to balance. So for the nitrate, I have 2. So I'm going to put a 2 here. And then actually by putting a 2 here, it is now balanced. So that's our A. So part A is actually nothing new. Part A you should be used to doing at this point from way back when to unit 2. Okay. B. So this is our ionic equation. So this is our first kind of new thing that we're doing. Okay, so what this means is anything that is AQ, we are going to write it out as the ions that are actually existing. So technically lead 2 nitrate, it doesn't stay together when it's in water because it's aqueous. It's actually lead positive 2 ions and nitrate ions. So you have to also be mindful though about how many of those ions you have. So imagine like you were writing a dissociation equation. There's 1 lead ion and there's 2 nitrate ions. So you're going to do the exact same thing to anything that is AQ. If something is not AQ, we're just going to copy it out so we don't separate it. So that's our first one. Then we have potassium and iodide, which is AQ. So we're going to have 2 potassium ions plus 2 iodine ions. You have to be mindful this 2 applies, remember, to everything that it's in front of. I'm running out of space, but those are my reactants, right? So we've taken care of, we've done this, right? That's like this section, and we've done this, that is this section. So now we have, on the product side, 2 potassium nitrate, and it's also AQ. So that means we're going to do 2 potassium ions plus 2 nitrate ions. Okay, and then this last compound is solid. So what that means is we're not going to separate them out. We're going to leave it together. Because remember, the separation is only when you have aqueous.